So we were talking about a number of terms related to device drivers. We talked about what device drivers were. It is March the 20th. Oh my, it's like the year just floating by. March 20th, 2025. We're currently in module 6, and we're going over some of the flashcards and some of the content related to devices and device drivers. All right. There's a first in, first out chip. Let's make this larger so everyone can see. And this is a computer chip that stores a small number of bytes or words that can only be accessed in order that the data was written. It is sometimes used to supplement input output device data registers. Let's go back to a data register. What is a data register? It's a register associated with an input output device in which the device driver writes data to that data that the device outputs and reads the data that the device inputs. I read that horribly. I'm sorry. A register associated with an input output device in which the device driver writes data that the device outputs and reads data that the device inputs. See register. Okay. I'm gonna show a video in a minute. A little too large. We were talking about words, and the last time we were together, I brought up the concept of binary. When I talked about what binary was for Internet Protocol version 4, routing a message, how binary is a base 2 language for computers, uses ones and zeros. For our messages flow or are transferred on what is called an Internet Protocol version 4. And with that Internet Protocol, we use bits where 1 byte is a bit or a binary digit. 8 bits is a byte. And that 1 byte is also called 1 octet. And in an IP version 4 message, you have 4 bytes, which are also called 4 octets. So So each one of these values, either a one or a zero, you have 8 of them, but you have 4 sets of 8 hits while you have 32 bits. So our messages have to flow on the 32-bit boundary. And I know that could be confusing for a lot of people, but we'll get to that. Each bit has a value. So you have 8 bits, and bits 1 through 8 can either be a one or a zero. But then there's a value associated with each bit. The first bit always has a value of 128. The second bit has a value of 64. The third bit has a value of 32. Fourth, 16. Fifth, 8. Sixth, 4. Seventh, 2. And the eighth bit, 1. So if you add all those up, you get a value of 255. So that's how they calculate your IP address. This is the binary version equivalent of your IP address. This is the value of 255. This is the value of 0. And then I will have to go through and calculate these 128 plus 32 plus 8 plus 4. And then that would give me a certain value. Then if I did 16, because this is 128, 16. So 16, anything that has a zero, you don't count the value. So this would be, let me go back to this again. I should make this larger. So this here would be 128. We would skip 64 because it's a zero. This would be 32. So 128 plus 32. We would skip 8. We would skip 8. Am I right? Where was I at? Oh, I'm sorry. So we have 128 here. We would skip 16, and we have 32 that we would use. We would skip 8. I'm sorry, we would skip 16. We would use 8 and 4 and not use 2 or 1. And then we'll calculate that value as such. So I hate to mess up my diagram, but 128 plus 32, because I'm skipping the value of 64. I'm not going to use that. I'm not going to use the value of 16, but I'm going to use the value of 8, value of 4. And for these two zeros right here, I'm not going to use the values of 2 and 1. Okay. So this would be the value of this particular, this is the binary equivalent, and we're trying to find the dotted decimal. I'll show a video that's going to go a little more into it. So let me second. I'm just adding it up. Plus 32 plus 8 plus 4. So that would be 172. So this first section, or what we call this first byte, would have a value of 172. Okay. The second byte, which we're going to use to calculate this value here, will come here, and this is going to be 64 because I can't use the 128 value. It's a zero. 64 plus, well, I'm not going to use 32, but I'm going to use 16. 16 plus 8. And then all the way on the end here, you have a value of 1, and that bit has a value of 1. So I would add 64 plus 16 plus 8 plus 1. Enter. And this is the value of 89. So this is the binary equivalent. So this is what we refer to as binary ones and zeros. Sorry for my Y not there. And what I'm trying to calculate below, we will refer to this as the dotted decimal. Dotted decimal. Okay. So that's what I'm actually calculating. I'm converting the binary equivalent into the dotted decimal. Bold, underline, blue, yeah, dark blue. Sorry. Any questions about that? I know it can seem confusing. I'm about to show you a quick video in a minute, especially explaining it this way and you not being, but, I know if you take the one of my other courses, there are binary classes in it. So, um, but the whole point of this is to me getting to the point of explaining what a word is. It says the number of bits. Now we just said a bit is a binary digit. Okay. Binary is what? What is binary for a computer? Can anybody tell me what binary is for a computer? Binary is a computer language. So the bit is the representation of that computer language. I was asking, what is a bit? A bit is a binary digit. The number of bits that usually corresponds with the length of a CPU's internal registers or the width of the data bus. Usually the word is 2 or 4 bytes. Okay. So said all that just to try to break down and get you to understand bits and bytes. Okay. You have port map input output, a method for accessing input output device registers in which the registers are separate from the computer's RAM address space. And I'm gonna show a video with this as well because talking about it and you know if we don't read through it, sometimes it doesn't make sense. Um, And special CPU instructions are required to communicate with the registers, which are also called ports. All right. So you have registers that are called ports. Right. Memory mapped input output, a method for addressing input output data registers in which the registers are mapped into the computer's main memory space, and the CPU uses the same instructions for reading and writing input output registers as it does for reading and writing RAM. Let's do this. Just come here. Here. All right. So, what is a register? Types of registers. We're gonna, I want something that's not too long. All right. This is might be a little more graphic right here.
So we've already established how we can use a D flip-flop here to store the state of an input line and retrieve it later when we need it, effectively just remembering the state of a particular line at a particular point in time as dictated by the clock input. But as we've learned back in combination logic, pairs of wires can be put together to represent larger numbers. And of course, that can be tied in with binary arithmetic and binary number systems to do a lot of really cool stuff with digital logic circuits like this. So it stands to reason then that if we can store a single bit in a D flip-flop like this, that there must be a circuit that can do the same thing with groups of bits. And indeed there is. The circuit that we are referring to, of course, is referred to as a register. Now the register does exactly what a D flip-flop does with a single bit, except it does it with multiple bits. So a group of bits will come in on the D input, and they can be saved and retrieved by the Q output when the clock signal goes high. So if we'll say maybe 0x81 comes in on the D input here, when that clock signal goes from low to high, that 0x81 will then get stored in the register and get presented on the output Q. So how exactly does one build a register then? How exactly does one create something that can store groups of wires instead of a single one? Well, remember the function for a group of wires is the exact same as the function for a single wire, just scaled up to, well, a group of wires. When we stored that 0x81 in the register, it was the exact same as storing the 1 on the first bit and the 0 on the next bit and the 1 on the third bit in the register, and then representing those same numbers on the output. Effectively, what we were doing is we were just taking a bunch of D flip-flops, and we'll just do this here with our inputs here and their outputs here, and we were just taking the C input of each of them and tying them together. That's it. That's the whole circuit for a register. So with all of these D flip-flops, each taking care of memorizing a single bit, with one pulse of the clock input, all of these D flip-flops will then memorize the input that they have been given and present that input on the output. On top of that, you can also have what's referred to as a controlled or an enabled register, and all that is it's basically the exact same thing as a normal register, except the output is controlled by an enable line. So if the enable line, we'll do this here, if the enable line is a 0, then Q is usually either going to be 0 in some cases, or in other cases it's actually going to be tri-stated. That's symbol for high impedance typically. That's more in electronics. We're not really covering that, but just for all intents and purposes, if E is 0, the output is usually 0 as well. However, if E is a 1, then Q is whatever is in the data register, and we'll denote data register as DR. That way we're not confusing with the D input. So whatever is stored in the register is presented on the output Q if E is a 1. Otherwise, it is a 0 or, in some cases, high impedance. And again, building something like that really isn't that difficult. Really, all this is basically just an uncontrolled register here. If I draw my clock, my data input, and my output, we can basically just take this and run it through a buffer. And that is basically our E input right there. And that's all that register is. It's basically just a normal register with a buffered output. So you might not think that having a controlled output on a register would be particularly useful. You might think that that's really not necessary. But I can tell you that there are many occasions.
Stop it here because, sometimes electronics can get a little out of hand. So let's go to this one right here, data registers and program counter. All right. Maybe I'll do this. Let me see this one.
Living with opioid addiction can be a struggle, trapped in a cycle of opioid use, withdrawal, and cravings.
Hi everyone, this is Fabi here, and in today's video we'll be talking about microcontroller registers. This topic, along with the topic of next week's video, which is going to be memory addressing, is really going to help you out when you're going to try and debug your code, and it's going to enable you to understand what's actually going on under the hood of your microcontroller. If you're new to the channel, this video is part of an educational series I'm doing, which is called Embedded Systems Explained, and the aim of this series is to actually explain concepts from embedded systems in a simple to understand manner and by giving you examples so that you know where these concepts are actually used in the real world. If you want to learn more about embedded systems, make sure to check out the playlist, which I'm going to link in the comment section down below in a pinned comment. So why should you bother learning about registers? After all, when you're writing C code for a microcontroller, you're not going to even directly interact with these registers. And that's true, but if you want to understand how your C code is going to run on your microcontroller, you need to take a look at how it's going to be translated into assembly first. This way you can figure out how you can write more optimized code for the platform you're targeting, and not only this, but when debugging your code, you're actually going to be able to look at the registers, and because you'll know what you expect to see in those locations, you'll be able to debug your code more efficiently. Okay, so first of all, what are registers? Well, registers are fast storage locations which are meant to temporarily store data which needs to be processed by the CPU or to store addresses pointing to data which needs to be fetched. Registers are different from cache as they are not meant to reduce average memory latency, but they are meant to store the current context of the CPU, so what the CPU is actually doing right now or the operands it's using right now. Let's now take a look at how registers are actually being used in a microcontroller architecture, and most resources online actually take a look at the 8051 architecture, and I think it would be useful to take a look at a different architecture for this video just so that you have a different perspective. There's not huge differences between the MSP430 architecture that we're going to take a look at in this video and the 8051 as far as registers go. There's obviously a few small differences, but if you understand what I'm going to talk about in this video, you're going to be able to apply it for pretty much any architecture out there. So the MSP430 has 16 registers, 4 of which have dedicated functions and the others are just meant for general use. These registers are 16 bits wide, meaning that the CPU will work with 16-bit operands. As you can see over to my right side, the first register, R0, is actually named program counter or PC, and its purpose is to store the address of the next instruction which the CPU is going to perform. The program counter gets incremented by the number of bytes the instruction has right after that instruction is actually executed. Apart from being incremented, the program counter can also be loaded with a new value, which can happen if there is a branch in the code execution. And such a branch could happen in case of an if-else statement, or if there's an interrupt which is being triggered, or in case of a reset event. The second register, the SP or stack pointer, is used so that the microcontroller can actually address the stack memory. This memory is actually used to store the current state of the registers in case the microcontroller needs to perform a separate task, for example if a function is being called or if an interrupt is being triggered, and to actually store the address of the instruction which is going to be executed right after we are going to return from this function or from interrupt routine. The stack works the following way. After a reset, it's going to be initialized with its maximum value, and it's going to be decremented whenever we are going to push something onto the stack, and then it's going to be incremented back when a value is being popped out of the stack again. This is actually what two of the instructions which are meant to work with the stack are called, and that is push to actually load something onto the stack and pop to actually take stuff out of the stack. The other two are call and and ret, and they are actually going to store the program counter into the stack when a function is being called, and the other one is going to restore the program counter when that function returns. As you might have been able to tell by now, the stack is a last in, first out mechanism, because what we are first going to take out of the stack is going to be the last thing we push to it. The third register, the SR or the status register, contains various status and control flags, and we are going to talk about each of them separately. 4 of these flags are arithmetic flags, and the first one we are going to talk about is the overflow flag. Now, this is being set when we are working with signed numbers and when the result of an operation with these two signed numbers is going to flip the most significant bit. The reason for this is that the most significant bit actually tells us whether a number is negative or positive, and if the result of adding two positive numbers is going to flip the most significant bit, this obviously doesn't mean that the result is negative. But if this information didn't exist and we just read the result from a register, it could lead to us actually misinterpreting the result. Just to be clear, this can also happen in case of subtraction, division, and multiplication. The next arithmetic flag is going to be the negative bit, and this is going to be set whenever the result of an operation is going to be negative. So essentially you can think of this as a replica of the most significant bit, because we just established that when the most significant bit is 1, it means that the number is negative. The third arithmetic flag is going to be the 0 bit, and this is actually going to be set to 1 when the result of an operation is 0, otherwise it's always going to stay 0. The last arithmetic flag is going to be the carry flag, and this is going to be set when the result of an operation is too big to fit into a register. So you can imagine if we are going to add 1 to the maximum value we can store on 16 bits, which is 65,535, we are going to get 65,536, which we can't store on 16 bits. And in this case, the carry flag would be set, which allows us to actually handle this situation correctly in code, which would probably be to store this on 32 bits. The content of the status register is always being updated after an arithmetic operation, and this actually allows for instructions such as JNZ, or jump not 0, or jump to X address if the result is not 0 to exist. Other status bits are SCG1, SCG0, and also
I have to say I really like this video because he's really breaking the content down. Here's one thing I have to say that about the new way that people learn. A lot of people don't like to read. And I'm sorry, in technology, if you don't read, you won't succeed. This is not a field where people are just going to show you. Now, I know we're in like this video education phase and things of that nature, but if you don't read, if you don't explore, if you don't really dive in, you're not going to learn. Cyber is a field where you have to. It's not a process based. Like you start out in a process, but after a certain process, you have to innovate and you have to change. But you got to go back and you got to learn. Now, what we did earlier. Let me come out of this video. Is we just went over some of the terms. Now, he's mentioned a lot of these terms and kind of brought life to it as well. You have memory mapped input output, a method for accessing input output device registers in which the registers are mapped into the computer's main memory space. All we're talking is about the processes. It's like a factory, and we're talking about the processes in which data and information or data goes into a cycle to be calculated to ultimately output as information. Okay. And that's why we say the CPU and the RAM is a big portion of this processing. We have programmed input output, a method for reading and writing data to an input output device in which the CPU must read and write each byte or word of data from and to the device register. We have direct memory access, or DMA, a method for reading and writing data to an input-output device in which blocks of memory are transferred to and from a device using a DMA controller with little involvement by the CPU. So then you have a device memory or direct memory access controller, and this controller will help the CPU to allocate memory as well as to process as well. You have random access device, a device that allows data access to occur directly to any location of the device's storage. without having a start at the beginning each time a data access occurs. We're going to get back to the video in a minute. We have a character stream device, an input output device that transfers data 1 byte or word at a time. And just think about taking your cell phone and plugging it into your computer, into your laptop, or anything like that. There's a controller that reads that information. But to process some of the things that are taking place, you have different registers that help along with that process. You have sequential access devices, which is what he mentioned before, which is what he mentioned before. Um, uh, just another announcement. If you have not taken a midterm, the midterm closes tonight at 11:59. I believe that. If not, it's 12 o'clock on Friday, but I think it's tonight at 11:59. Gives me time to grade. So what's a sequential access device? A device that requires data to be accessed in the order in which it is stored on a device. This is where we talked about last in, first out, first in, first out. Just look at it as a factory, a conveyor belt, things going in a certain way, following a certain procedure, a process, and then there's a delivered output. And then you'll have different devices that are going to monitor and measure how things are performing, like a status register. Input output range, a range of memory addresses used to temporarily store data that is transferred between a computer device or component and the CPU. Remember, all this is about input output devices, devices, and device drivers. You have tar files, a Linux file format in which multiple files are grouped into a single distribution file. It's a compression file. So, like if you were to go in Windows and compress a file, you would get like either a 7-zip or you would get the your compressed file. This is similar to that. You have loadable modules, a device driver in Linux that is not linked to the kernel, but is loaded when the OS is started. You have device special files, a file used in Unix and Linux for managing input output devices. The file can be one of three types: a block special file, a character special file, and a named pipe. Block special files. In Linux, a file used to manage random access devices that handle blocks of data, including DVD drives, hard disk drives, tape drives, and other storage devices. Remember when we showed the hard drive? Let's do partitioning. Drive. I'll use this one. This is good. Just gotta wait for it to process. Boy, here we go. All right. So here's a hard drive and the components of a hard drive. And just think about the different sectors and the information that will be stored on sectors or different blocks of information. Now I brought this up just to be a representation of what we're talking about, but we're really referring to RAM and the CPU. But I just wanted to just bring this up to represent that. All right. We'll get back to him in a minute. To show you that it says you can manage random devices that handle blocks of data, including DVD drives, hard disk drives, tape drives, and other storage devices. You have character special files, an input output management file in Linux used to handle byte by byte streams of data, such as through a USB connection. So all we're doing is we're just taking a micro approach to understand computing and how data travels and how the components work to travel to compute data. because it's important to understand that if you're going to protect a network. You have named pipes. In Linux, a device, special file for handling internal communications, such as redirecting file outputs to a monitor. Now, when we talk about a pipe in Linux, a pipe is a command that if you enter a certain command and you enter the pipe command, which is right above your enter key on your keypad. If you look at your keypad, you'll see enter, then you'll see a slash, and then you see this line going, this vertical line. That line is called a pipe. Okay. So if you enter your command and enter that character, then um, direct that command to send that file to a certain place, then that is how that will work. Or when I say how to work, that's what that command will do. Let me just show you very quickly. Pipe command in Linux. They also call it a redirect. All right.
When you type a command in, you'll typically see some kind of output. But what if you wanted to do something with that output? Maybe you want to save the listing of a directory to a file. This is exactly what redirection and piping allow us to do. Redirection allows us to redirect input and output of commands to and from files, as well as connect multiple commands together into pipelines. Piping allows us to send the output of one command as the input of another. Now you can start to picture how we can use both of these to create pipelines, and it's actually quite creative because this means that there are multiple ways to get to a very similar result. Let me show you. Let's start off with redirection. So first I'm going to just list a directory that I have. It's going to be the user bin directory. And you can see there's a bunch of details in here. What if I wanted to save this to a file? Well, this is something we can do with redirection. Let's type in that same command. ls stands for list, the -l stands for long, so it's a listing with more details. And then we're going to provide that same directory. And this time we're going to use something called the redirection operator, which is the greater than symbol. Finally, we're going to provide a file name for our output to be saved to. I'm going to go ahead and hit enter. Now this is a new file, so it gets created. But say you already had this file and you run this command, since we're using the redirection operator, it's going to get overwritten. So if I do this cat, which will just output the contents of the file to the screen, we can see it's the same as what we got before when we actually listed to the screen. We do have the option to append, so say we do something like hello, echo hello, and then in this time we'll use the append redirection operator, and we'll provide that same file name. Now I print out the contents, and we can see it's the same, except at the end, the hello was added. Alrighty, let's take a look at piping. So I'm going to clear the screen. Using the pipe operator, which is this one right here, the output of one command can be piped into the input of another. Let's use the list command with the head command. So what we can do is type in ls-l of that same user bin directory that we've been using, pipe operator, head. There we go. Might be able to make this a little bigger so it's easier to see here. Alright, so you can tell that from the first time that we ran this command where we listed straight to the screen, we got a lot more of output. The output in this case is 10 lines, and the head command lists a certain amount of lines of output.
All right, so I just wanted to show you, like, when they're saying piping, this is what, think of it like irrigation. Like, when they work on bridges, they're really not just working on a bridge, they're working on the irrigation infrastructure. So you'll see them changing out these big tubes that are really used to transport water from place to place. That's piping. You can do the same thing in theory with your contents in Linux, as well as Windows. You can have a report that you're going to make every day, but you need to pipe it to a certain file or a section of the hard drive. So you can create a folder and you can pipe those outputs every day to a certain area so that you can run reports. So that's what that's referring to. Does that make sense? Anyone? If it's confusing, please let me know. And some of this takes when it's new, it takes a while to get used to it or actually learn it. But that's what in this term here, when they're talking about piping, this is what they're referring to. Okay. In Linux, a special device file for handling internal communication, such as redirection or redirecting a file output to a monitor. That's what they mean by pipes. So that's a name pipe. You said I'm going to need to go over this a lot, but I think I have the basics of it. Okay, good. Here we have a network attached printer, just a printer that has a network interface. It's connected to the network and can be accessed by computers on a network. We talked about earlier in this class, we talked about client server networks. Client server networks will have one dedicated printer or maybe a few dedicated printers that a group of individuals are all going to print to. That's a network printer. It's connected to the network. And it will have a host name or an IP address. Okay. IP address is the host name. Print queue. Print queue is a temporary file used to store a print job until it can be sent to the printer. So basically, there's a section of memory where your print jobs are held, and they're held there until it's ready to go to the next job. Once you line up in queue, then the next set of items that are to be printed will then be directed to be printed next, but it will sit in queue. You have a print job, the data or the document sent from an application to a printer and accepted by the print spooler. All right. A print spooler. What is a print spooler? A process that accepts print jobs from applications, stores them in the print queue, and then sends them to the printer when the print device is ready. Has anyone ever if you have your printer at home, have you ever had it where your computer just did not print? Then if that's the case, sometimes you will have to bring up the print, if it'll let me. You have to bring up your print spooler. And see if it'll let me do it. Sometimes you can do it that way, or sometimes you can just right click and go to Task Manager. And if you go to Task Manager, you pull up Task Manager and you can go to your services. Those extensions. This is a different layout than there we go. You can go to services, and if you go to services, then you can scroll down to the print spooler. That's if it's here. Sometimes you just have to bring up services. All right, so it's not in this window here. It would have been around here. So sometimes you have to go and pull up services. I feel like I'm mistyping. I did it right. So I don't know if you can see. Let me see. All right. So here's the print spooler. Um, Not the print spooler, but this is the services that are taking place behind the scenes on the computer. If I scroll down to print, and we can find the print spooler. See, there it is right there. And it's actually running. If I click on it, and then if I right click on it, you get a list of options. You can start, stop, pause, resume, restart. You have all different tasks. You can even refresh. Sometimes you have to refresh. Sometimes you have to start and stop your print spooler, and then you can print again. Okay. So just little things that have happened. That's why I said a lot of learning about technology is experimentation. So these are issues that I ran into, and I had to find the answer to it. I was like, why is my printer not printing? And then I would go online and I would find these things. This is before I started teaching. So, and I would be like, why is my printer not printing? Okay. And then it would give me a list of options. A printer might not print due to reasons including low toner, connectivity issues, paper problems, problems with the print driver or print queue. Then I would start looking up, wow, let me see the print queue. Now we're using generative AI, and generative AI, a lot of people don't like it, but it gives you a list of options. Back in the day, you had to go to Microsoft and figure out why, especially if you got an error code or something like that, then you have to put your error code in. But it's all about experimenting. All right, next one, a block special file, which they brought up already. So this is one of those terms that just keeps coming up. In Linux, a file used to manage random access devices that handle blocks of data, including DVDs, hard drives. Remember, we read that one already. And we read character special file already. Loadable module. I don't know why it's on here again. A name pipe. We went through those. Device special file. So those are the terms and terminology that's associated with this particular module. Now let's get back to the individual. Here, I guess it's the FabYTM. All right. So now it's going to go a little more
Later off, all of which are responsible
into those terms and concepts.
for the clock signals that the processor or the peripherals use. We are going to talk more about these in a future video in the series. The CPU off bit stores the current state of the CPU, so if the CPU is, for example, off because it's in a low power mode state, this bit is going to be 0, otherwise it's going to be set to 1. The general interrupt enable bit can either enable or disable maskable interrupts. So if this bit is going to be set to 0, basically all maskable interrupts are going to be ignored. There are some non-maskable interrupts though, such as those that happen when we are trying to access a forbidden memory location or when an oscillator fault occurs, and these can be disabled, hence the name non-maskable. The third and fourth register also have a more unique use as they can be used to generate commonly used constants. This might seem like an unnecessary feature, but when you're thinking about how often you're going to use constants in embedded development because of all of the bitwise operations that we are going to do, this actually brings a significant performance boost. Moreover, this is actually done automatically. You don't need to write any code to enable this feature. Registers R4 to R15 are general purpose registers, and it can actually be used as source or destination operands for most instructions available. You will see these registers being used to implement the logic you've written in C, or you will use these directly to actually write your own assembly code. Given that there are 12 of these 16-bit registers, we can optimize around the idea of using these registers as much as we can so that we actually avoid accessing data from the memory that often. Though these are 16-bit registers, by appending a .b to the instruction we intend on using, we can actually work with 8-bit data. I'll give you a short example. So let's say we've written the C code to my right, so we defined and initialized an unsigned int variable named a with a value of 3. Then we are going to define a new unsigned int variable named b, which we are going to initialize with the value of a. Now let's actually take a look at what this would look like in assembly. First we have the move operation, which moves data from one place to the other. 3 is going to be our source, and R15, a general purpose register, is going to be our destination. This actually tells us that the value of the unsigned int a variable is going to be stored in R15. The reason for the .w appended to the end of the instruction is because we are working with 16-bit variables, and just like I told you that .b means that we are working with 8-bit variables, .w, which comes from word, means that we are working with 16-bit variables. The reason why a occupies 16 bits is because it's an unsigned int, and ints usually occupy the same amount of space as CPU registers, which in this case is 16 bits. The second instruction is add, with the first operand being 7 and the second one being the content of R15. The result is always going to be stored stored in the second operand, so in this case in R15, which is where we just established that the variable a is being stored. The third instruction is going to move the contents of R15 into R13 because we just defined and initialized a new variable b with the value of a, and actually R13 is going to be where this variable is going to reside. In next week's video, when we are going to talk about memory addressing, I'm going to explain exactly why we have the hash sign before the numbers you just saw in the example. You should also know that most peripherals also have their registers, which allow us to actually interact with them, enable interrupts, check for flags, and stuff like that. If you want to experiment with what you learned today, pick up an MSP430 development board or any other board with a microcontroller, write some C code, enable the generation of the assembly code as output from your IDE, inspect this assembly code, and then start a debugging session so that you can actually check.
I just want to ask this one question. What is an interrupt? I want to make sure I get a good understanding of that. Make sure everyone understands that. What is an interrupt? Think about CPUs. This is content that we've talked about in the class already. What is an interrupt? In terms of a CPU, what is an interrupt? Get your Google on. Another way to phrase it is an IRQ, an interrupt or an interrupt request. Yep, I said interrupt. When y'all give me responses, I need y'all to give me a response like you understand it. I like that. All right, I'm gonna explain it this way because I want everyone to get it. Here's what an interrupt is. You have a number of processes that are taking place behind the scenes. Just to show you, I'm gonna pull up Task Manager once again. Let's see here. Right click, Task Manager. It's always gonna ask me to input my password. All right, so I'm going to pull up Task Manager because I want you to see all the processes that are taking place behind the scenes. All right, so here's Task Manager. Now, just Task Manager, I have the processes selected now. These are all, you have my main programs that are running. These are my apps. Then behind the scenes, you have all these background processes that are taking place. And these background processes, multiple processes, are associated with a number of programs. Man, if you run Google, look at all this Creative Cloud. If you open up Google and you see all of I look at all the instances of Google that is open. That's why people don't like how a lot of guys that are into people that are into computers and processing technology and help desk, they don't like all the resources now that Google takes because I don't have that many Google instances open, but they use a lot. This is why you see energy efficient because you have to set up your computer that if you're not using a certain process in Google, it'll shut Google down and those resources will stop. That's why you see 0% here being used. Even though it's in memory, you see 0% being used. Your account needs attention. Anyway, but you have all this stuff taking place. All right. But these are so when we're talking about an interrupt is just saying you have these processes that are talking to the operating system that are going to say, hey, I need more resources to work. And to do that, it's going to send an interrupt request. And that request is going to go to pin 1 of the CPU. A request that alters or halts the execution code that provides instructions. Absolutely. It's going to go to pin 1, and then the CPU is going to have a conversation with the operating system. And then the operating system is going to look over the entire computer, everything that's taking place, and see and prioritize what needs resources and what doesn't, and then try to fix the situation. This is why we talked about preemptive and cooperative um, operating systems and um, computing when we first talked about operating systems in the first module. Okay. Going back to module 6. So that's pretty much what our, you know, in terms of the terminology, what we're actually getting into here. Okay. So understanding that there's input drivers, there's input output devices, there's you have your South Bridge controller, or you have your input output controller, and you have data registers. You have a number of things that take place to monitor the process of how information is computed and how devices interact with the operating system. So this chapter says you will be able to describe how OS or operating systems communicate with various categories of input and output devices, explain the need for these device drivers, install device drivers, and install printers as well. All right. So here, let me minimize my screen. Okay. You'll There are different categories. In this module, we'll focus on input-output tasks like handling input from the keyboard, mouse, or other input devices, handling output to the screen printer or other output devices, controlling information storage, and retrieval using storage devices like disk drives. When I listen to this stuff, I think about us in our world as well, and how you have computers that emulate what we do. Think about going to the post office and you all have to line up in queue to deliver packages. And there's a process that the post office uses to ensure that they're going to send the mail to the direct or the right address. So everything follows that process. When you want to go get something to eat, you got to get in line, and then get in that line, you have to follow that process. And there's a process that the fast food organization is going to use to make sure that you get your delivery on time. So it kind of follows that. How are we going to communicate as devices? Communicating with remote computers through a network. So you have a register, a storage location associated with the input output device that data can be read from or written to. So a register is a storage location. This would be kind of like your what's those places? I forget the name of the storage companies right now. Similar to that, where your information can be written to. You have your input output controller, reads commands written to the control register and performs the requested action. Remember, you have different types of registers. What's the control register? This is where the device driver writes commands such as read or write for the input output controller to act upon. Then you have a data register. This is where the device driver writes data that the device outputs and reads data that the device inputs. So you have a specific box where input and output information is going to be that's going to be read. Okay. We have a status register, indicates the device driver whether the device is ready to accept a command, that is, the device is busy, or that an interrupt has occurred. Most control and data registers are a byte or a word in length. And we say that's either 16 or 32 bits or bytes, excuse me. And that's why I brought up, even though it's IP addressing, I brought up addressing right here. We went into, because we're going to get into this in a particular chapter anyway. What's a MAC address? What's an IP version 6 address? What's an IP version 4 address? When we get to networking, we're going to talk about those. Here it says in some cases, data registers might be supplemented by a first in, first out chip in which multiple bytes or words of input or output data are stored in the order they were received. So first in, first out. And this is an image of you working on a Windows application and having a device driver such as your hard drive have this application communicate with this particular hard drive. You have port mapped and memory mapped communications where you can use dedicated memory addresses referred to as ports and special CPU instructions to communicate with input output devices. Then you have memory mapped. I know we're going back over the definitions again, but still. The control and data registers are mapped into the computer's main memory space, and the CPU uses the same instructions for reading and writing input output registers as it does for reading and writing RAM. Okay. Then we have programmed input output devices and direct memory access. So here it says input output devices that require the CPU to read and write each byte or word of data from and to the data registers are called program input output devices. Modern computers use a process called direct memory access or DMA to transfer large blocks of memory to and from an input output device with little involvement by the CPU. Just imagine you connecting your cell phone to your laptop and then you're doing certain processes like maybe you have an iPhone and you have iTunes on your laptop and you can like transfer data. This is the process that we're describing when these sort of commands happen. You have your what's here. It says most input output devices can be categorized based on the following: how data is accessed and how much data is accessed. 1 byte per transfer, or a block of data per transfer. You have random access devices and sequential access devices. Random access allows data which accesses the system to occur directly at any location of the device's storage without having to start at the beginning each time a data access occurs. Sequential is just going to be in order. This includes serial ports, network interfaces, and tape drives. In order to access a data or the data at a location, 100 on a sequential access device, it must first pass through locations 1 through 9. Like going in the airport before you can get to gate 99, you got to go through all the gates to get through certain. That's why the larger the airport, sometimes the more frustrated, unless they have a tram. You have device categories, such as your character stream device, um, which transfers data at 1 byte at a time. Keyboards, mice, serial ports, and sound cards are examples of these. And then you have block devices, which has collections of bytes, which uses a fixed size. Storage devices are the most common block devices because they can hold blocks of data. And network interface is a special case. It most closely resembles a block device. A network interface could be a router, could be a switch, could be a hub, could be a multitude of different devices. Why an OS needs device drivers? Remember, we talked about the kernel. The kernel controls software and hardware. You have to be able to control both. So the operating system provides basic input-output support for devices, but it doesn't support specific features of each device. And then for that, you need a certain device driver to help the operating system. Advantages of drivers. You have OS specific functionality that's built into the kernel, and new devices come on the market without requiring extensive updates. That's why a lot of times when you get a new device, you plug it in, the computer starts looking for the drivers so that it can effectively run merge hardware and software. The number of input output devices can expand to offer users a broad range of device selections as well. All right. Just trying to bring a little category to this. All right. So I'm going to put this on a pause, and I'm going to let you continue and read through the rest of this. I don't want to be the reader. I want to be more or less. But in order to understand some of the questions that you have in this chapter, so if we go to the activities and here, thinking case projects. All right, so installing a printer. And then you go through these things here, like it says, Hard Rock makes hard candies that are sold worldwide. One of its specialties is fruit flavored candies such as papaya, guava, grapefruit, kiwi, orange, banana, and watermelon. Hard Rock employs 328 people and makes extensive use of computers and networks in the business. Users in the business office have Windows 10. The Candy Kitchen staff all uses Mac OS, while the shipping unit prefers Fedora Linux. Sheesh. The IT unit uses Fedora Linux for its own desktop computing needs and supports 8 Windows servers, 2016 servers. The business office has just reviewed 3 new laser printers for installation and wants to train the printer support coordinator to install the printers for Windows 10 computers. The laser printers have network interfaces and must be connected to the network. The printers are named Laser 1, Laser 2, and Laser 3. The business office has 3 rooms with a network attached printer in each room. Describe the steps required to install the printers in each room. Lord. So, in that critical thinking activity, what would I recommend? We do the following. Now, one thing they're always going to tell you is to download your drivers first. When it comes to printers and connecting printers to a network, you're going to download your drivers, which is the first thing you're going to do. Network printers on a network to a network. All right. So here's to install a network printer, ensure it is connected to the same network as your computer. Okay. And you do that by making sure you have the correct IP address. All right. As well as same subnet mask. Then use your operating system's printer management tools to add it to the printer. Either automatically or you want to network printers, you want to manually do it. You don't want to do it automatically. By entering the printer's IP address and host name. So in other words, you want to make sure you have a network connection, and you want to open your printer settings, add the printer, do automatic detections. Everything is online. So that's how you would answer that question. If you've ever connected something to your computer, since you don't have a network app, this is the way you would do it. But if you do have a printer at home, it's the same in theory, just a little different. Okay. So even for troubleshooting, it tells you how to do certain drivers. Now let's take a look at this video.
Like this, and here we have this add a device
We're gonna go from the beginning about here.
control. Or any version of Windows, we're going to add the network printer in a very simple manner. So click on the search icon and type control. You will find the best match control panel.
Now let me say this is for client computers, but if you were in a real job, you would have to log into the server's control panel and access the server control panel. Will we explain? No, just give me a blanket explanation. You don't have to go into great depth for each type. The requested alters. Okay. People always.
And I will click on that, and here I will get all control panel items, and we need to click on this view by and click on the large icons. So once you click on large icons view by, you will see a window like this whether you're using Windows 10 or Windows 11. Now here we are looking for devices and printers. So I can see here the devices and printers is there, and I will click on that, and very soon a new window will appear like this. And here we have this add a device, and we have this printer and scanner. So I will click on that, and then we get an option add a printer or scanner, and I will click on add device. And the moment I do it, it will start refreshing, and it will start looking for the network printer if you have in your network. However, if you do not get that, you will get an option to add a printer manually. The printer that I want isn't listed. So I will click on add manually, and here we have this option. My printer is a little older. Let me find it, or select a shared printer by name. So try the second method first. Select a shared printer by name and click on browse, and here you will have your network automatically, and you can select your printer if you see a printer here. If you see it, well and good, select that, click on select, and then next few times, and you will have your printer added here. If you do not see that, you can go with the third option which says add a printer using IP address. So for that, you need to go to your Wi-Fi, the router, to know the IP address of your printer. If you know, well and good, you can simply enter the IP address of that printer, and you need to click on next, and your printer driver will be added. The fourth option is here. Let me just click on that. Add a Bluetooth wireless or network discoverable printer, which is my favorite option because this is the most successful option here. And you need to click on next, and it will start searching for the devices over the network. So if you have a printer added to the network successfully, you will see the printer here, and you can add it from here. So once you're done, you just need to click on next, and your printer will be listed right here, and you can make it default by just clicking on that, and you can run the troubleshooter. You can print a test page, and you can try that. So these are the steps which you can follow. And also check here, let me open up the file explorer, and here we have this network. See if you have other computers and printer here. If you do not have it, then you can search from here, go to the router page, and see whether your printer is connected to the router or not.
Ladies and gentlemen, that's all I have for today. Do you have any questions? All right, remember there's going to be a summary, which I'm going to create right now. So look at what we've covered so far. We've looked at operating system fundamentals. We've looked at client server operating systems. We looked at the CPU, which we've been talking about it quite a bit. Filing systems, installing operating systems, which we covered in chat this week. And now we talked about device and device drivers. So, and how the CPU and RAM are associated with those drivers as well, and the different types of categories and registers that are associated with devices, device drivers, and the CPU and the transfer of information. And the summary from Tuesday wouldn't allow me to write. Yes, I went ahead and I fixed that as well. Tolupe told me when she came in, so that's now fixed. And I'll put an announcement in the class in regards to that. So now you should be able to, and you don't have to worry about submitting to that. I'm excusing you from that because you weren't there for that particular class, so don't worry about having to do that assignment. That was the one that's in module 5. You don't have to do that one. All right. So I'm gonna go ahead and enter this one in. Class assignment. This is the end of class. Today is 2/20. I like to go here and grab it. So now y'all seeing how I create assignments.
When is the end of class thing due?
Um, I've been giving y'all more time than I used to. So as long as you can get it in as soon as possible. Um, and if you have not completed the midterm, please complete not the prep. Some people completed the prep, think that's the midterm. Please complete the midterm. You have additional opportunities, but yeah, you have. I've been extending it, so just try to get it in. I would say at least try to get it in at least by Monday. You know, let's have it in by that time.
Also, thanks for the extension for the midterm.
No problem as well.
Okay.
Oh, and chapter 5 has been reopened. So if you didn't or you weren't able to submit or complete those assignments, I took the due dates out. It's still open, but the due dates are there so that you can have time. And I know it's a lot of these types of case studies and things of that nature, but you know what? I'm gonna save that statement and leave it to the end of the class, and then I'll explain some of the things that I do. All right. So we also begin module 6. Nope. Delete. All right. So this is the assignment. 30 points. Use 6. There we go. All right, everybody. If there are no further questions, class is dismissed.
Take care.
No problem.
Did you extend for chapter 5?
Yes, I opened all of, as you can see, there's no dates here now, so all that's been extended.
Has it? Okay.
Yeah.
So we have 2 summaries now instead of just one.
Now you did the one summary for every course has a end of summary. So the end of summary for module 5, we went over module 5 or that day. Each day I give you that we meet, I give you a summary. So
Hmm.
you got to give me a summary. I got to make sure it doesn't necessarily, it's like a check for understanding.
Yeah.
Yeah. So, yep.
Okay.
And I may start throwing in little stuff to see if people are paying attention. I'll be honest with you. I like online teaching. I don't
I
like
do as
remote
well.
teaching.
Makes my day easier.
It does. But what I notice is some people like to cook, watch TV, tend to their animals, surf the internet, do different things.
Yeah.
And I feel like I'm wasting time, when I could
And that's
just,
why you get these summaries as a way to, okay, let's see who's paying attention for real.
yeah, basically.
Hmm. Okay.
Even though anybody can just go along and they can say, you know what? But if they mention something I said, then I know that they've been paying attention.
All right.
Okay.
All right, I'll get chapter 5. Yeah, I basically I think I did the midterm, not 100%.
Is it just us on one? Because I don't want to. Okay,
Yes, it
good.
is.
All
Yes, it
right,
is.
good. Let's go to
I think I did do it. I'm not 100%. I think I
I
was still
think you
waiting
did
on,
the prep.
did I? Um,
Yeah, let me go back and see
No,
because
because I thought I
midterm exam, spring prep. Let me go back and do this.
exam.
And speed grader. I could be off. It could be someone else. Marco. See, you did the prep.
Wait, wait, let me see.
Now, here's what we could do. Here's what we could do. I could go through the prep and
Oh,
see if you got everything right on the prep. Grade that and bring that grade over here where you wouldn't have to redo it.
okay.
You're fine with that? Then,
Um,
oh, go ahead.
sure. I know I did one of them.
Yeah. The looks like you probably did the prep exam.
Did I?
Uh,
No, I
modules.
thought I. No, wait. Did I do the final accidentally?
I hope not. I don't think I have the final available. I normally have a date and a
No.
final.
Okay, no.
Yep. Yeah, I have a date and a
It's.
final.
Wait, was it this one?
Midterm. Let's go
Yeah, it
here.
was midterm prep,
Yeah, I think that's what you did.
and I did it on the 11th. I did it on
Yeah, if I go here, speed grader, and
the
I
grade
put my name
incomplete.
right here, you did the prep. So this is what I'll do. I'll read through this. I'll go through this. If you did good on the prep, I'll take that grade. If
Well, yeah, I had
um
to grade the rest of them
yeah,
because.
so if I go through this and just let me know if you're happy with that grade and you still if you're not, you can do the midterm prep and I'll just push the grade over to there, you know.
Okay.
All right. So yeah, I guess give me about 10 minutes. You'll see a score populate. And
Okay.
then if you're happy with that, then you can go with that. If not,
Okay.
we'll work with it.
Also, I like adding bold texts in some of my thingies.
Oh no, that's fine.
Okay.
That's
I just
cool.
wanted to make sure.
Okay. All right, I'm gonna go ahead and grade it and then I'll get back to you. I'll send you a message.
Okay.
All right, cool.
All right. See you.
You have a great one.